A park ranger driving on a backcountry road suddenly sees a deer frozen in their headlights. The ranger, who's driving at 11.4 meters per second, meaning that is the initial velocity, immediately applies the brakes and slows with an acceleration of 3.80 meters per second squared. So now you see that they are slowing, which means it's a deceleration. If the deer is 20 meters from the ranger's vehicle when the brakes are applied, how close does the ranger come to hitting the deer? So this is a good example of why you should draw a diagram instead of just plugging values randomly into an equation, because you need to know what you're actually doing. So let's look at that. So we have the ranger here, and they are going at 11.4 meters per second, and this is when the brakes are applied. So there's the deer here, and so they're moving and they see the deer and they apply the brakes and stop the vehicle before hitting the deer. So when they're stopped, it is 0 meters per second. So if the deer is 20 meters from the ranger's vehicle, where is that distance at? Right? So let's look at it. It's from when the brakes are applied to the deer. So it's from brakes are applied to the deer. So this is our 20 meters. So how close does the ranger come to hitting the deer? So that would be this distance d. So that's what we want to know. So let's do this question and see what is the distance between the brakes applied and stopping. Because if we can figure out delta x, this distance here, then the distance d between stopping the vehicle and the deer is 20 minus delta x. So let's look at part A. We have v0, which is 11.4 meters per second. Final velocity is 0. We have A, which is negative 3.8 meters per second squared. So let's look at v squared equals v0 squared plus delta a plus 2a delta x. So we have 0 squared equals 11.4 meters per second squared plus 2 times negative 3.8 meters per second squared times delta x. So that gives us delta x equals 17.1 meters. Now what we want to find is the distance d. So distance d is 20 meters minus 17.1, and that gives us 2.9 meters. So the second part is how much time is needed for the ranger's vehicle to stop. So what is the time between the ranger stopping and the brakes applying? So what is this distance t here from here to here? So this is why it's important to draw a diagram. So let's do part B. V equals V0 plus AT. So V is 0. V0 is 11.4. Deceleration times t, and that gives us t equals 3.0 seconds. It's very important to draw a diagram so you know what's your starting and stopping point, because these two equations we are using from brakes applied to the stop positions and not to the deer. But the distance they are giving you, initially 20 meters, is from brakes applied to the deer. So you cannot use 20 meters directly in an equation, because we are using brakes applied to the stop positions for our equations.